There we go. Right. Okay, so we're going to continue now. So if you look, we're on page 46. Okay. Do you want to stay there, or do you want to move back? Mohammed and Dana. You can stay? All right. Don't be sad. Soon. Don't be sad, okay? It's okay. She's not far away. It's okay. Right. Work, energy, and power. This is 8 now, but it's a single instead of a double. You know the reason why. Okay, so we have to start off firstly with some definitions of these terms. So the first one is work. So I suppose you could say work always happens when there's a force, that the two really go together. Okay, so when there's a force applied to a mass, we say some work is being done. Okay, so if you want to think about it like this, for work to happen, we need a force.
Excuse me, do we have like any definitions or explanations in here in this book?
Oh yeah. So, for example, a simple idea is you have somebody pushing or lifting something up, yeah? So to do this work, you need a force. Okay? So, work and force, they're very close. But there are different. They are different, but, you can think in your head, if there's a force, there's some work being done. Or, if there's work being done, there must be some force. Okay? Work doesn't just happen. You need a force. Okay? So work is done when a force moves a mass. I mean, that's the definition in the book, and it's given as a formula. So if you want sort of a definition, we can say work W is done when force F
moves in the direction of
moves a mass M in a direction. I'd say not in a direction. Mass M by a distance, let's say S. And I should note, please note, this formula, this definition, the direction for F should also equal the direction, the displacement, direction of movement.
So it's F as
If it's not, yeah. So in the simple case, you have a mass M and a force F moves it, and the formula for this simple situation is just force multiplied distance. So this force, let's say, moves it a distance S. How much work is done? That's how much work is done. That's the formula. Force multiplied distance. Who knows the unit for work? Yeah, the unit is joules, which I think it'll say there. It doesn't. Yeah. One letter for joules? Oh yeah, that's another way of doing it. Yeah, I think it's small j.
No, big J. Capital J. Capital J.
You're saying that with too much confidence. All right, capital J.
I
Yes, capital J. The unit is J for joules. So sometimes you need a formal definition of joules. Whoops, sorry. So if you want, oh come on, where's it gone? Okay, so 1 joule of work is done when 1 Newton moves a mass a distance 1 meter. 1 meter. So if I ask you how much work can 1 joule do, well, 1 joule of work is 1 Newton moving a mass 1 meter. So, you know, that sounds like a lot, doesn't it? 1 joule can move or can make a mass move 1 meter with a force of 1 Newton. You know, that's pretty big. Okay. So that's work. Now, it's not true if the force and the direction are at an angle. Okay, so we'll look at that one next. Can I go down? Not yet. Did you write this down? Yeah, okay. So if we have this situation, the block is moving this way, but maybe the force is being applied this direction. Again, just like with our turning force, you can think about it like this. We could break the F up into X and Y. If this is theta, how big is this F here? Yeah. Now, we don't care about this force because all this force is doing, well, it's not making it move because it's perpendicular. This force has no effect.
Sir, is that the force is applied that way, or is the tension is being pulled?
No. Well, if you think you can think of it as a string. Yeah, the force is being applied in that direction. Yeah. This force has no effect on moving it horizontally. It's only this force, isn't it? Yeah. So if you have this situation, then the formula just becomes this: work is F cos theta times the distance. In that case. So actually, Tal, the definition of joule is in the book. If you wanted to see it, it's on page 46. Do you have it there?
I found
You found it, yeah. So it says 1 joule is the work done by a force of 1 Newton when it... Okay, it's very, very technical. But in other words, 1 Newton on a mass to move at 1 meter is 1 joule. Yeah.
So, work on moments, they have the same formula.
Well, this is... Yeah, actually, yeah, it is the same formula. That's true, yeah. You have your force. The only difference is the meaning. Here, S is the distance moved, whereas in the moment formula, it's the distance from the turning point, not necessarily how much it moves. Yeah, but the structure, yes, is the same. Yeah. Okay, so let's look at a graph here. Can I go down? Yeah. Okay. So what we have here. Let's draw a graph, and here I'll put force and distance. Okay. So here is force, and then here is distance. Now, in the real world, it's not normal just to have a force pushing a block and then that's it. In the real life, it's more complicated, isn't it? So, for example, like here, whoops. So if we think of our man here and he's pushing. So what formula could I use here? W, yeah. Work equals Fs, isn't it? But, you know, when he gets here, he needs more force, doesn't he? He pushes harder, and then here he goes back to just like this. But maybe he's tired, so he pushes less. And then here, he needs a lot of force to get it over this. Yeah. So let me draw the graph, force and distance. So at the beginning, he has a force. And then it's constant. Then what happens here? It increases, doesn't it? And then what happens here? Yeah, and I think realistically, it'll probably be less than here, because he's tired. But then what happens at this piece here? Yeah, he probably needs the most here. And then when it gets over the top, yeah, he probably stops, so then there's no more force, so it'll go right down to 0 then. Okay?
No, like the last line should be straight, vertical.
This one here?
The very last one.
Here?
Yeah.
No, I'm picturing him slowly coming to a stop. Like,
So,
you know, he doesn't just get to the top, stop, and then jump away. Yeah? Yeah.
He brought the block in a constant force.
Yeah.
And so you put a straight line.
Yeah, if I want, I can label it. So if I call this part 1, 2, 3,
So
4.
in the part 3, he's going straight. So why not the graph just breaks down like straight?
Oh, here it is. This is part 3.
Oh, then
Yeah, and this is part 1, and this is part 2, and then this is
why
part
is
4.
that part 2 is like this?
Because he needs a lot of force to get it up. But then as it's coming around here, he can relax and then go down to a lower force here. Anyways, the reason I'm showing you this is because in the real world, this is what happens with a force. You know, it increases, it decreases. It's not the same. Tal. Now, in this situation, we could use this formula, but it gets very complicated because you have different forces and different angles. But if you have the graph, this area here, the area of this graph actually equals the work.
Oh. So why is that?
Why is that? Well, if you think about it, what unit is distance?
X.
Meter. Yeah, meter. Yeah. And what unit is force? Newton. So what unit is the area? Meter Newton. Yeah, and if I go back here, what unit is this? Yeah, the same, Newton meter, isn't it? Is a joule. So you can think about it like that, Tanish, that the area has the correct units for work. Now that's not really a proof, okay? That's just more of a kind of explanation why. But there is a complicated proof.
Would that be like a question with graph and after find what done based on graph?
It's not happened, but I mean it's possible, because in the physics exam there's always one graph question in section B. So they would get the student to draw a graph, and then they would ask the student a question about the graph. So like, for example, if it was Newton, they might say draw the graph and calculate the distance travelled, which would be what on the graph? It would be the area, wouldn't it? So if I said draw the graph for the force and calculate the work done, it would also be the area. Yeah. It hasn't happened, but I think it's a possibility, yes. Okay, so that's the graph, force and distance. Okay. Can I scroll down? Do you have that? Okay, so that is the first one, work. Okay, next now, energy. If a body or a mass okay, so this is simple definition to start with.
So can I just define energy as capacity to do work?
Yeah, capacity to do work, ability to do work, yeah. I'm trying to keep it as simple as possible. So I'm saying if a body can do work, then we say it has energy.
So it means that the work is a measure of energy.
They're nearly the same thing, and in fact, in a lot of questions, they are the same thing, really. But essentially, yes, if something can do work, we say it has energy. How much energy it has equals how much work it can do. Okay? So, for example, if a body can do 1 joule of work, yeah, it has 1 joule of energy. It has 1 joule of energy inside of it, almost. Okay, so example here. This person here, let's pretend he has 100 joules of energy inside of him. So what could he do? He could push 1 kilogram with 100, well, it doesn't need to be 1 kilogram. He could push this mass with 1 newton for 100 meters, or he could push the mass 1 meter with 100 newtons, as an example, okay? So he has 100 joules of energy, so he can do different types of work, but notice how the total work must still be 100. Okay, so that's the idea for energy. Okay. Can I go down? Yeah. So then the last one here then for definitions is power. Power is work, rate of change. Yeah, I'll just write it as power is work done per second, or as you were going to say, Tanish.
Rate at which work is done.
Yep, that's it. Or another way of saying it is power is the rate at which work is done. What's wrong? As a formula, you have it like this. Power is how much work is done divided by how much time is spent doing the work. So this here is work done, and then this one here is time spent doing the work.
Isn't it capital P?
That is a capital P. Let me capitalize it more and boldface it and put a little stand on it. I don't know. And I think the problem is my equal sign needs to be lower down. Okay. Can I scroll down? Not yet. Do you have that? Yeah? Yes?
Yes.
Yeah? Okay. So, I want to give you an important example to think about. So there's 2 situations. So, here is 1,000 kilograms. Oh, let's make it a little bit more realistic. 10 kilograms. Hey, and this person takes 10 kilograms up the top of the hill. They push it up. Okay? And then this one here, this person here takes 1 kilogram up. Okay? And then they jump back down and they take, jump. Yeah, so Yeah, we can do a parachute or something, okay? The reason I say jump is that they don't walk back down. There's no energy used. They just jump back down. So they do this 10 times.
So is that both of them?
It's different situations, yeah. Okay, so in the first case, a person takes 10 kilograms to the top, and the second case, a person takes 1 kilogram 10 times. Which one has done more work?
Equal.
The same.
Same work.
Same.
Same work. But which one has more power? More power.
The lower one.
The first one. Because they both have the same work,
Oh yeah.
but this one probably has a smaller
Time taken.
time, yeah. So when you calculate the power as work over time, this one I think will be bigger. And the reason I show you this example is to be careful not to confuse power and work, okay? There's actually the same work done, just different power here. Alright, what's the unit for power?
What?
Yeah, unit of power is watts or joules per second. We can use both in physics, okay?
Can you say in
So can I use what?
Yes, if you want.
So what?
Yeah, yeah. That's fine. Yeah. Okay. Can I scroll down? So we're going to look at today two important types of energy, kinetic and potential. So if we think about it, this is mass m and its velocity v, and it's moving. This could do work. And I'll make up an example. It's a silly example, but just to give you the idea, okay? Suppose I have a box here and I need to break it. So if I want to break it, I have to put some force on it. Remember? So remember I said if there's a force, then there is work. Yes? But of course another way to break the box is I can just throw this ball at it.
So, which is a force there as well.
Yeah, yeah. If something is applying a force, then that something is doing work. So we say it has energy.
So could you repeat that?
If you push the wall.
Yeah, now it gets complicated because the wall, it's not moving, but what you're doing is you're kind of breaking bonds, and that's a different type of work and energy. That's a difficult example, yes, yeah. So, work is a force and a distance, but sometimes the distance you can't actually see it. So like for example, if I break this with a force, what's the distance? Well, there's no distance because it hasn't really moved. But there actually is a distance because if you think about it, there's all these atoms in here with the bonds. So if you look at it in a microscope, what you have is an atom, and there's a bond. And when you break them, of course, they move, I mean, we never do that in physics, okay? It's too complicated. We just deal with simple situations where you push something and it moves. That's all. But I still want you to understand the idea that if there's a force, there's work. Okay? So if I'm pushing here, I'm doing work. You can't calculate it because you can't see the distance, but I'm still doing work. Okay? Here is easy. Okay? A force and a distance, and I did work. That's easier. Okay? Anyways, I want to break this box. So if I want to break the box, what do I need? I need a force. Yes? But I can throw the ball at it. And you could work out how much force. Remember, I think in one of the homework questions, it was actually the ball hitting against the wall, wasn't it? Yeah. So you could work out the force, but I'm only talking about force because I want you to picture if there's a force, there's work done. Okay? So if something is moving, it can do work. So if it is moving, it can do work. So it has energy. So this ball has energy. So we say it has kinetic energy. This mass has energy, and it's called kinetic energy, or just Ke. And you can actually work out how much energy it has. The amount of energy it has is a half mv squared. So how much work could it do? Well, that much. A half mv squared. Okay, so that's your first formula. Yes, trillion. Okay. So I remember I said there's two. Potential then.
MGH.
MGH, yeah. Hey, come on. Now, if you think here, is this moving? No. But if I drop this, it could break something, yes?
Yeah.
So again, it could do work. Right? So again, it has energy in it. So, it has energy in it because it can do work. And in this case, we call this energy potential energy. So we have a mass here, and its height is h. We say it has potential energy. Yes. Well, for this type of potential energy, yeah.
So,
Yeah.
if there's a ladder
Yeah.
on the wall,
Yeah.
and if a person is lifting some box
Yeah.
above, and if they were to ask what's the work done, it's MGH.
Yeah.
And the H will be this one.
Yes.
It's not the
Yes. Yeah. Okay. Yeah.
Can you give a short definition for potential energy?
I can. Yes.
Potential energy, kinetic energy.
Say again.
Isn't potential energy equal to kinetic?
In certain situations, which we'll do shortly. Yeah. So a definition of potential energy. If you want a technical definition, you would say
energy possessed by an object with respect of.
yeah. I'm trying to keep it.
Energy stored in people, yeah.
It's stored. Yeah. I'd say potential. Do you mind closing the door? Potential energy a mass has due to being in a. Now, see, to give you the definition, I have to give you words you don't know. Force field. So, a force field is any situation where there's a force being applied that you maybe can't see, like gravity. Another example might be magnets, electricity. Yeah, that's called a force field. Anyways, you have potential energy when you're inside one of these, because you think about it. This has energy because the Earth is pulling it down. Okay, if this was in space, outer space, no more potential energy. Okay. Also, if you think about it, a magnet, north-south magnet, that could pull something. Again, it would have potential energy. We don't do this formula. We just do this formula, the gravity one. Okay. Yep. Yes. Go ahead, Jeff. Right. Let's have a look. Oh yeah, and famously, before I go ahead, we have this very important rule. Very important.
One person out there.
So what does that mean, MG?
Very important. Conservation of energy. It's a bit like conservation of momentum. Okay. Energy is not created or destroyed.
So
Yeah, actually, I wonder what they go for in the book.
So basically, the loss of kinetic energy equals to the gain of potential.
Energy is not created or destroyed.
Yeah, actually, I'll keep it. Yeah, I'll keep it simpler. Energy in a system is always constant. And I'll use this now for some examples.
So if there were in exam, we'll be asked to define the conservation of energy.
Yeah. That's fine.
Is that-
Yeah. Okay. Example now? Yeah.
Is that it? Energy.
If you want, if you told me it cannot be created or destroyed, yeah, that's great. I'm just trying to keep it simple for right now. It's like conservation of momentum. The before and after energy values are the same. Okay, let's have a look at an example now. Can I go down? Yeah. Okay, so let's say here we have a person here, okay, and he throws a ball up here, and it lands up here, and this is 100 meters. And let's say the ball, I'll just say it's 0. Yeah, I was going to go with 2 to make the half cancel, but I'll go with 0.5 kilograms. And when the ball is up here, let's say it's going at 2 meters per second. So I would like to know what is the speed here. So, wait. If you think about it, this is the before, and this is the after. So the kinetic, the energy here is the kinetic energy plus the potential energy. Here, oh well, just take it as it starts on the ground, okay?
100 meters is too much.
Yeah, you're right.
So what's O2 up there?
What?
It's a ball.
No, I'm sorry, that's the ball again. Right. Now, kinetic energy is a half v squared, which we don't know. And the potential energy?
And
0, because the height is 0. It's on the ground. Yeah?
It's 10 meters.
10. No, here, before picture. Here.
Oh,
Here. And then here, energy is kinetic plus potential. So the energy is a half m what do you say? 2 squared plus potential energy, which is m g h. Okay. Yeah? So can you tell me what this is here? This will be 1/4. What is it, Joshua? 50 point, huh? The total. These two add together. Yeah, what you got, Joshua? 50.91? 50.05? So we'll just say 50 joules. Is that okay? Is that right? Yeah. Okay. So, conservation of energy means the energy at the start should equal the energy at the end. Yeah, what's square root 200? About 15, is it? Less than 15. Oh yeah. 14.14. So that's how fast the ball's going. Okay. Yeah.
Why did we add the potential energy?
Ah, because it's total energy.
Well, it was still moving up, so
Oh yeah, but it's moving higher. So it's moving, it has kinetic, and because it's higher up, it also has potential. It has both. Yeah. I want to give you one to try. Yeah. Because this is important for the exam. Okay, so here. 0.1 kilograms and 0.1 kilograms, of course, and it swings up here, and here it stops, and then it will swing back down. It's a pendulum, yeah, very good. And let's say this height is 0.10 meters. Okay. I would like to know the speed here, the v, to make the pendulum swing up to this height. So again, you can say the energy here must equal the energy here.
Isn't there should be an angular speed?
Say again?
Angular speed.
Oh no, we don't need to consider that. That's the great thing about this formula. It simplifies a lot. So tell me the v. Work out the v for me.
What's G?
9.81, please. Yeah.
So is that 1.4?
I don't know, I haven't worked it out yet. 1.4 also?
Yeah.
Yeah? Okay. So there's another example I want to do. So you said a half 0.1 v squared equals 0.1, 9.81, 0.1.
Yeah, there's no kinetic because it stops out there.
Very good, yeah. So this is what you were saying, Mohammed. The kinetic at the start will equal the potential at the end then.
Yeah.
That you asked me earlier. Okay. Now,
In the case previously there is a
yes, there is, yeah. Yeah, is what Joshua was asking me. Now, I'm going to do an example now that's like this, but a bit more difficult. Okay, so I'll give you the information here. Okay, so what you got here, a bullet of mass 0.01 kilograms, and its velocity is 10 to the 2, so 100 meters per second. And it's moving along here, and then it crashes into this block here, and its mass here is, it looks like it's quite big, 990 kilograms. No, sorry, no. I meant 0.990 kilograms. Yep, okay. And that's on the end of a string. And then what will happen here? It will swing up. To here. And we would like to work out Our question is, what is the height here?
Oh,
Okay. So do you understand what's happened here?
when the bullet hits the moment,
Yeah.
the momentum of the
Yes.
of the bullet reduced.
Yes. You've answered my first part. For the beginning, we think of this as a momentum problem, a collision problem. So what we have here is the momentum here before the collision equals the momentum after the collision. So before they collide, what's the momentum before they collide? So it will be, 100 times 0.01 plus 0. Because this is moving and this is not. Yeah? Then, after they collide, what happens to the bullet? It gets stuck inside. And then this starts moving with speed v. What's the momentum of this? Well, what's its mass? 0.991. Because the bullet is inside it.
0.01.
Sorry. Oh, sorry, that's 10. Sorry. So it'll be,
1 0.
oh, it'll be exactly 1.
1 1.
Yeah. And its velocity? Its velocity? V. So 1 times V is V. And this here is 1. That's very nice. So the momentum before is 1, and the momentum afterwards is V. So therefore V equals 1. So here V equals 1 meter per second. Now, somebody tell me, for the second half, when the block swings up, why can I not use conservation of momentum? Why is it not allowed? So I could use conservation of momentum for the start, but why can I not use the conservation of momentum for the second half when it swings up?
They're just opening.
Because the bullet sticks to the
No.
messing to
No. Now remember, I said for conservation of momentum, there must be no force. When it is swinging up, what is the force? Gravity. So no conservation of momentum. But before they collide, they're just like this, right? Well, this one's not moving. It's just like this. Is there any force here? No. There's no force here. It's horizontal. But then when it sticks in and swings up, there is a force because of gravity. So we can use conservation of momentum for the start. So what should we use for the end? Conservation of energy. So what energy is at the start? Kinetic. Any potential? No. And then at the end? Potential? No kinetic. So let's see what we get. So what is the kinetic energy at the start? It's a half mv squared. So a half mv squared, plus 0, that's potential energy, equals kinetic energy plus potential, which is mg h. Okay, so it looks like h would be quite small. 1 over 2 times 0.981. What's that, about 0.05 or something? Or what is it? 0.05
0.05.
meters. So 5 centimeters.
So could you repeat the process? First include the momentum.
Yeah, so first, I'll write it here. From here to here, conservation of momentum. So the momentum before the collision equals the momentum after the collision. And then from here to here is conservation of energy. The energy here equals the energy here.
conservation of momentum, are we finding the change in momentum or the
Momentum before equals momentum afterwards. Or if you want the formula you showed me earlier today,
yeah.
this one is what I'm using. You showed me that earlier. That's the one I'm using for conservation of momentum.
And you're finding the V.
Yes, I'm
The
finding the
after.
V. Yes, yeah. Yeah.
And,
Okay. Any other questions for this one? This is a very common physics question. I've seen this in the exam as well. So the answer is 5 centimeters. Yeah. Okay, did you write that down? Can I go on to the next one? Okay. So here's another example.
Wait,
What?
one person didn't raise it.
Is that person you?
Wait. No.
Okay, then I can go back. Who needs to write this down? Okay. So here, Tanish, there is my conservation of momentum calculations, and then here to here, that's my conservation of energy calculations. So this was kinetic, potential, kinetic, potential.
could you show the conservation of momentum part with using the formula?
Yeah, if you want me to fill in the numbers, is it?
Yeah, just
It's
using
M1 U1 plus M2 U2 equals V M1 plus M2. I'm using your second formula you showed me.
Why is that second one, not the first one?
The
The first one is elastic.
No. The first one is when the masses do not stick, and the second one is when the masses combine together. Yeah, okay. I don't know what vocabulary you want to use, but the second one is when they combine.
Together, it's, that's
That one.
so,
Okay. Can I scroll down now? Can I go down?
Yeah.
Okay. Right. Here's another example. So, we have here, imagine there's some water here, and let's say it's moving at 2 meters per second, and we'll say it's 3 kilograms per second. So it's water moving in a pipe. Then what happens is there's some pump, and it pumps the water up a hill or up a building or whatever, and up the top here, and then the water comes out.
Did you come up with it by yourself?
No, I've seen this in the exam twice. Yeah. Okay. And we'll say we'll put this as 100 meters. So my question, or the question is, what is the power of the pump?
Does the speed of the water increase after the pump?
Yeah, no, these are good questions, yes. So what we'll do is we'll assume that the water just about makes it to the top of the hill. So we'll say that it's nearly zero, the speed, if you want. Okay.
Where?
At the top here when it comes out. Okay. Well, I don't think it can actually be zero, because if you think about it, if 3 kilograms of water go in per second, then how much water must come out here per second? It must also be 3 kilograms. So we know that it's 3 kilograms a second here. Now the question you said, Joseph, is it going faster or is it going slower? Well,
since it's pumped, so
it could be going faster, could be going slower. We're not so sure. But we don't really need to know that. We could assume that it's just going at the same speed to make it easy, okay? So let's say it comes out at 2 meters per second as well. Also, we don't know if the pipe is bigger or smaller as well. We don't know these things. But anyways, We'll just assume it comes out at the same speed. Okay? Right, so what's the formula for, yeah?
What do we need to find?
The power of the pump. Okay? Well, before we find the power, we could find out the work. Yeah, so the work.
So isn't the work on the right side? Since
Yeah, well, what's the work here?
mg.
Yeah, the work is just mgh. Because if you think about it, what has happened to the water? It's gotten higher.
Yeah.
So it got potential energy. Now, you know what? I'll start this again because you're looking a bit confused. Okay. I'll draw it again, but come on. I've used up all my undos. Okay. It's ugly, I know. Oh, no, sorry, that's too ugly. Let's try this again. There we go. It's a pipe. Okay. Right, so if it's 3 kilograms a second, this is the way I always picture it, okay? I picture the water in like big blobs of 3 kilograms. Now, yes, I know, and you know, that is not how water moves, all right? But it's easy for me to picture 3 kilograms a second as 3 kilogram blobs per second. So each 1 second, one of these blobs move, okay? And then up the top, we have the tree as well, moving along as well. And again, it's 3 kilograms. Okay, so let's imagine we look at this one here. So here's our pump. So we're talking about 1 second. Okay? How much water goes into the pump in 1 second? 3 kilograms. Oh, and what was its speed? I said 2 meters per second. So its speed is 2 meters per second. So we could work out how much kinetic energy it has. What will it be? A half v squared.
So it's 2 squared. So it's 4.
Oh, sorry. Yeah, so it's 4 then. So what will that equal? 6 joules. So that's how much it has. It has 6 joules when it gets into the pump. Now, think very carefully. Very carefully here. If 3 kilograms go in, listen. If 3 kilograms go in 1 second, then how much must come out in 1 second? 3.
It's 6.
Oh, I mean,
Yeah, no. It's important that you think about this, okay? If 3 kilograms go in 1 second, then 3 kilograms must come out in 1 second. Because it can't be more. Why not? Because where does the water come from? And it can't be less. Because if only 1 kilogram came out in 1 second, what's happened? Maybe 2 kilograms is still inside the machine. Yeah? It's like people walking down a hall. Okay? If 5 students go in the hall, like a hallway, then 5 students must come out. If 5 students don't come out, if 2 students come out, then what's happened? There are 3 people still in the hall. And if this keeps happening, what will happen? It gets stuck. Yeah? Okay? So, I would say here, 3 kilograms go in 1 second, and 3 kilograms go out in 1 second. Okay. So I think that's clear, right? You're okay with that? Yeah. Now, will that be enough energy to get the water to the top?
No.
No, the pump has to give it some energy now, doesn't it? The pump has to put some energy into it so it can reach it to the top. How much energy does it need?
as much
As much
potential-
energy as it gets
potential
from potential energy. Yeah. So what is the potential energy of that 3 kilogram blob? It's mgh. So what's that? Work it out, please.
What's the height?
The height is 10 still. 10.
2,994.3.
Right.
Oh, 10 meters, not 100.
Yeah.
200.
Yeah.
294.3.
So up here, the energy, what did you say it was? 2,000?
2,994.3.
200?
294.3.
294, 294.3 joules. Now what's the kinetic energy up here?
Zero.
No, because remember my logic of if 3 kilograms go in, then,
6 joules.
6 joules.
yeah. So here it must still also be 2 meters per second. Now again, if it was not this, then that means the water is getting stuck in the pipe. Yeah, so we need this also. Okay, so what's the energy at the bottom? The energy at the bottom
6 joules.
is 6 joules. And then what's the energy at the top?
300.3.
30.
3.3 joules.
Yeah. Now there's a problem here. The energy before does not equal the energy afterward. But it does, because it gets energy from the pump. So the pump puts energy into the water so it can push it up the pipe.
So we also can the pump the energy from.
Yes, the energy from the pump. So we can say 6 plus the pump must equal 303.4. So how much energy do we get from the pump?
So it's
Yeah, it's actually going to be the same, isn't it? 294.3.
And what is the question?
The power of the pump. So that's the work of the pump. But that's per second.
So we divide by 1.
Yeah, so divide by 1. So then the power, which is work over time, so that would be 294.3 over 1. So that's the power of the pump. It's 294.3 watts. Now there's another way to think about this. Okay? The other way to think about it is, I am down here with my mass and I want it up here. So it has gained mgh. So you could just say that. My 3 kilograms, I've moved it up to the top. So it got energy. How much energy did it get? mgh. Where did it get this energy from? Yeah, from me, from the pump. So the energy it got was from my work. My work I've done is the energy it got. So you could just say W equals mgh, and that's fine too.
Instead
But-
of 6 plus pump and all that.
Yeah. But the reason I did it this way is for you to really appreciate what I'm saying here. Is the energy at the bottom, which is the kinetic plus the pump, equals the energy at the top. And what's the energy at the top? The kinetic, the kinetic plus the potential. Okay, so you can think about it like this, as in energy before equals energy after, or you can just think about it like what I said at the end. That if I move 3 kilograms up, this got energy from me, so the energy it got is the work I did. Donna, you look very confused. Are you okay? Right, is that a yes or a no? I'm not sure.
Why the 300?
Oh, you can't see it, sorry. It's up
No,
the...
no. You have a
300.
mistaken calculation this way.
What?
You're on 303.4, but it's actually 300.3.
Oh, I misheard then. It's 300.3.
Yeah, but it doesn't matter because after that you magically subtract.
Yeah.
There is answer.
300.3.
303.
Yeah.
303.3.
Oh, so it...
No, it's not 303. It's just 300.3.
300.3, thank you.
Really?
Yes. 300.3.
Please calculate.
300.3. Okay. Is that better, Donna? All right. Now, continuing. Yes, yes. A little bit of vocabulary now. So, anyways, there's three formulas for work, energy, and power. First formula, kinetic energy. What is it? Half mv squared. Potential energy, mg, and work. Yeah, force by distance, or yeah, that's it.
Power.
And power. Yeah, that was the other one. Power. Work over time.
Yeah.
Yeah. Okay. Now a little vocabulary here. Okay, so we have our collisions here. So this is our U1 and our U2, and then M1 and M2. And then afterwards, we'll just say M1, I'll just put it this way, V1, and then let's say it's going this way, V2, M2. Okay. What is the energy before they what the heck? What's the energy before they collide?
M1.
No, energy. It's just kinetic, isn't it? A half M1 U1 squared plus a half M2 U2 squared. That's before. And then after, a half M1 V1 squared plus a half.
So it's negative.
No, well, but it's squared, so it'll be positive. Okay. Now, I'll write three statements down. Energy before is equal energy after. Energy before is less than energy after. And energy after is greater than energy before. Okay, I want to know which is true, which is false. So the first one, yeah, it could be true. Second one is false. And then this one here could be true. Now, yes, sorry, I wrote my B's and A's the wrong way around, didn't I? Thank you. Okay. Now this one is true because what's the name of this rule? Conservation of energy. This one is false, but this one can sometimes be true. Look up. This one can sometimes be true. What happens is the following. When they collide, they make some heat. So some of the energy becomes heat. So the kinetic energy here is smaller than the kinetic energy here because we have some heat, for example. So we could say energy before equals energy after plus heat energy. Or noise energy. Or some other type of energy.
So where does the heat comes from?
So it's like, yeah, actually, do you remember this? When you rub your hands,
Yeah.
it gets warm. So it's from friction, maybe. But you can see if you make heat or noise, then some of the kinetic energy is lost. So then that's when this one could be true. The energy before is bigger than the energy afterwards. But just to be clear, to be very, very clear, when that happens, it's only the kinetic energy. Okay, that is very important. This is still always true, even in this situation. Energy before equals energy afterwards. But you can't have kinetic energy before being bigger than the kinetic energy afterwards if some of the kinetic energy is changed into different energy.
Could you explain it to me?
That's what I was
No,
doing. Yeah.
I don't understand about the kinetic.
Yeah, let me give you an example. Okay, so look there. Now, this has kinetic energy, this has kinetic energy, and they have potential energy. Okay? So if they stay here and they crash, maybe the kinetic energy is still the same afterwards, okay? But imagine that they crash, okay, and then they change their height as well. Then some of the kinetic energy changed into potential energy. So the kinetic before does not equal after because they also change their potential. Okay, so let's see. If this goes down, what happens to its potential energy? Increase or decrease?
Decrease.
Okay, so look here. So kinetic, and then let's say they crash and go down. So do they have more or less potential? Less potential. So do they have more or less kinetic? More. Now if they do this, okay, they have more or less potential? More. So do they have more or less kinetic? Less. So some of the kinetic changed into potential. But the energy before, kinetic plus potential, still equals the energy afterwards, kinetic plus potential. Okay? So what I'm saying here is that the kinetic energy can change in total. Okay? And there's some vocabulary. So let me write the vocabulary down now. Can I scroll down? Yeah. Okay. So if kinetic energy before equals kinetic energy afterwards, we say it was an elastic. Joshua. If kinetic energy before is greater than kinetic energy afterwards, we say it was an inelastic collision. The energy is conserved. The kinetic energy is conserved. And then inelastic would mean some kinetic energy was lost.
We'll have this question in homework.
You possibly have it in homework, and I have seen in the exam, the question would say, is the collision elastic or inelastic? So how would you work out if it's elastic or inelastic? What do you have to do?
Elastic is before, it was after.
Yeah, but how would you check? Well, you just calculate the kinetic energy and see if it gets bigger, smaller, or stays the same. Okay. Right, now.
Homework.
No. I need to do just one more thing. What? Hey, half this class is not in my good books. Right, so don't anchor me, please. Don't want to get all Bruce Banner Hulk on you, okay? So just please. You wouldn't like me when I'm angry, I promise you. Okay, so just one more thing to do here. Did you write that down? Yep, okay. So we're just going to finish off with collision in 2 dimension. Okay? I'll just do one example to show you how it works. So, let's say we have here, come on, 100 or 1,000 kilograms, and then here, let's say 2,000 kilograms, and here 10 meters per second, and then here 10 meters per second. And that goes there, and then they crash and move off that way.
Together?
Together, as one mess. And how big is this mess now? 3,000 kilograms. And its velocity, its speed, we don't know. And that's what I want to know. How fast does this mess move away? Okay, so, in fact, just like with the projectiles, you should look at this. You should think of this as an X and a Y. Okay? So if I just talk about X, what's the momentum before the collision here? It would be 1,000 times 10 plus, and what's the momentum here? No. 0. because remember, I'm just looking at the x. Yeah? Now here, what should I do? I should resolve. So this will be v cos theta, and this one here, v sine theta. Okay, and so what is the momentum after the collision? It'd be 3000 v cos theta. Okay, now let's look at the vertical. So what's the momentum here? 0. Plus here? Yeah, 2000 times 10 equals 3000 v sine theta. So we end up with this situation. We have v cos theta equal, 3000 v cos theta equals 10,000. So that means v cos theta would equal 3.33 roughly. And then likewise we get 3000 v sine theta equals 20,000, is it? So 20,000, so that's 6.66, is it? Yeah, yes, 6.67. Now we can put these together. So we could say V equals 3.33 over cos theta, and V equals 6.67 over sine theta. So that means 3.33 over cos theta equals 6.67 over sine theta. I'll have to end up getting both anyways, but we only want V. So if I rewrite this, I can get tan theta equals 2. So can you tell me what theta is, please? If I rewrite this one, yeah. 63.5? 63.5. Okay, so all I do now is take my answer and put it in here, and I got my V. Okay, so V is what?
So what did you rewrite?
Sorry, I rewrote this. I skipped a couple of steps into this. You can simplify it.
Is it like sine divided by cos?
Yeah. No, I have faith in you, Tanish. If you rewrite this later, you will get this. Yeah, it's like what we did with the projectiles. What is V? 7.45 meters per second. Okay. Now, we could also work out if the collision was elastic or not as well. So we'll do that really quick. Yeah, but we need to work, in the exam we'll say show. So we need to show it, okay? So kinetic energy here, a half m v squared. What's that, please? Can you tell me? And then this one here, a half, yeah, what is it? 5,000. Okay, and then the other one is a half m 10,000? Are you sure?
50,000.
Yeah, I think you're missing a zero. 50,000 and 100,000. So total is 150,000 joules. Now, after the collision, it's a half, what's the mass? It's 3,000. V squared. Yeah, so what's that equal to, please? What is it? Well, I feel confident in thinking that it'll be a smaller number than
So we
this.
should find the V, right? That's the
Yes.
Yeah, didn't we just want it 7.45?
Yeah, and adding on an extra piece. Yeah. So
Yeah,
can you?
it's smaller.
Yeah, what is it? Can you tell me?
83,253.75.
Okay. So kinetic energy before is bigger than kinetic energy afterwards. So therefore, we can also say the collision is inelastic. That's the reason. What's that? Heat. I'd say if you were looking at this wreck afterwards, it would be much warmer than what it was beforehand. And also noise. You know, it makes a loud bang when they come together. That energy has to come from somewhere as well. So heat and noise. Yeah.
The kinetic before is
150,000 from the two cars.
from the two.
Yeah, I'm talking about the total. Wait. Total kinetic.
Because this big half m, which is 1,000, and v squared, which is like for the horizontal.
Yeah.
And what is the vertical?
No. Just to be clear, kinetic energy has no direction. You shouldn't say horizontal and vertical. Okay? Momentum, yes. Velocity, yes. Acceleration, yes. Kinetic energy is something inside of the mass, so it's not important which direction it's moving.
I mean, so how do you calculate the kinetic before?
Come on, you know how. A half mv squared. That's the formula.
Yeah, I know, but the m is 1,000.
Yeah.
and- Okay.
Shh.
Energy is skeletal.
Yes, the scalar, yes. Half 1,010 squared plus a half 2,000 10 squared.
Okay, yeah, that's
That's it. Homework. Okay.
So next week.
Well,
Friday is the next one.
If we had tomorrow,
we have tomorrow, don't we?
Yeah. Sure.
not tomorrow.
We don't have time to do it.
But your maths homework doesn't need to be ready until Monday. And you, yeah, and
Smart home.
the maths homework I give you every night. And do you have chemistry homework?
Yes.
How much?
No.
No. Be honest now. What are you asked to
We
do?
don't remember.
No, seriously. She said
not
to be like,
Yeah,
most
she's
people
going
are
to be
email, it's like,
Because there's no enough paper, so millions I want.
Yeah.
And the man,
Yeah. Hopefully never give me.
It's probably going to be awkward.
Okay. I'll tell you what. What we'll do is, you notice how, yeah, well, it's not, well, okay, ultimately, for physics on Tuesday, I will want everything in the chapter finished. Listen. No, wait.
We're listening.
I need to concentrate. Everything, including the parts that you skipped in the previous question. Yes? Now, I would like everything done by Tuesday, but for tomorrow, if you could, let's see, you should have had up to 17 done, and it goes up, okay. So if you just did, no, 8C, yeah, if I look at the ones you've skipped, what ones have you skipped? You skipped number 11C, wasn't it? C11C?
Yeah.
And also, I think somebody said there was one of the questions I had. Oh yeah, 13 part 2.
no, 15, but no,
And 13 part 2, yeah. And 15 part B. Yeah. So anyways, for tomorrow.
No, we did 13 food.
Yeah, okay, whatever. What else? For tomorrow, I would like everything up to and including 19. Okay?
Okay.
Everything up to and including 19.
Okay.
Right? For tomorrow. But for Tuesday, it needs to be the whole chapter. Now, if you get it all finished for tomorrow, that's great. Okay? As a minimum, 19. As a minimum. Okay. Are you clear on your
Yes.
homework?
Yeah.
Mohammed, Joshua, and someone else. Tanish.
so I've done.
So, what about you?
Yeah, including
The
19.
videos are on Google. Now, if you want to see me in the teacher's room, if something's confusing you, if you want to work through some examples
I
together,
mean, from a physics tutorial or something. Change the class to a tutorial.
I'm thinking about it. Okay. Listen. Tomorrow's class for physics will be a tutorial, like in maths class. So I won't do anything new tomorrow. I'll just work on exercises from the book, from the beginning of the book. So if you have any questions from anything, tomorrow is your chance to get it answered, okay? Yes? Dana? What class is tomorrow? Thank you. Tutorial, okay?
So I've got a question. So
Wait, hang on, let me just stop the video here.
the class of
You done?
that's yeah.